Let me make sure Carl is here.
Actually, while we're waiting, Frank or Richard, can you say a little bit about how you want to spend? We have an hour and a half, I think, first of all, right?
Right.
Yes.
Right.
So,
is there a structure? How long would you like me to speak?
I mean, we can if you can speak for about an hour, and then we'll save the rest for Q&A. But I mean, if anyone wants to jump in for quick questions while you're talking, that's also fine too. But I think discussion we wanted to have today was on this terminology of solid state fusion, or whatever ideas that we want to talk about in terms of something that's a little bit more appealing to the public,
Right.
in context of ICCF, and then also the contests that we're putting together.
Right. Okay. And for me, just to fine tune the talk a little bit, how much have you had other sort of workshops, or where are people at in terms of their background about? I mean, I can make it very educational, or I can, if there's certain areas where where everyone's on board, then I can skip over those. So I just want to be mindful.
So most of us here, I think, are probably leaning on the social designer communications aspect of what we do. We do have a few engineers and scientists here as well, but probably if you could kind of give the high level conceptual aspects of the liner, you know, equations would probably not be necessary for this discussion.
Right. Okay, you know what, let me check in. I have certain sort of waypoints in the presentation, and so at those we can check in, and people can choose whether we go more into depth or we move on to another perspective.
Sure. And if there's like a concept that seems a little bit yeah, more specialized, yeah, maybe I'll interrupt once in a while, but other than that, I'll try to let you talk without any interruption.
Yeah. So I have definitely more slides than we have time for, so we can definitely choose at some point which way to go.
Yeah. If anyone does get really lost during a lecture, you're more than welcome to use the emoji to do this, where you just have no idea what's going on.
All right, very good.
So can somebody ping Carl? Because I know he said he was already here, but I don't see him.
Yeah, I don't see him either.
We were just in a meeting with him. Come on. All right, I'll take care of this while you guys start.
Okay, great. Okay, so we have a very special guest here, a longtime colleague of ours in the field of LNR, and also a longtime researcher in this field. So we have with us here Dr. Florian Metzler, who is a research scientist at MIT, conducting research with Professor Richard Lester. And so his background has been in nuclear engineering, but has also transitioned into quantum science that includes LNR, and now is also looking at aspects of technology management and how we can enable innovations to get out there quicker. And so previously he was a postdoc with Yet-Min Chang's group at MIT, and as some of you may know, he was also one of the participants in the Google-funded study that was published in Nature. And prior to that, he was a student with Professor Peter Hagelstein, who is one of the stalwarts in LNR and has been active since its beginning. So Dr. Metzler, thank you so much for joining us here today.
Sure, thank you for that kind introduction. It's my pleasure.
And so today, I think you're going to start our discussion with a historical background of Eleanor, and then if we have time, some discussions on some of the current work you're doing, and some broad discussions on the terminology around Eleanor.
Yeah, we should definitely do that during the discussion. I have the slides I prepared are grouped into two major sections. One is more of an introduction of what nuclear fusion is, what solid state fusion is, and how what was the original motivation to think about that direction, and what are some of the issues, the material systems, and so forth that we're dealing with here. And I think it's quite educational or pedagogical, so I hope nobody gets lost. But if you do, raise a hand, or if it gets too much into detail, we'll move on. And then the second part is taking a step back from that. The first part is essentially posing a lot of questions that are questions that are around today in society, in a sense. You know, what about, what is it? Why is fusion so difficult? What about, is there any evidence? What is the evidence for solid state fusion or LENR, and why is it so controversial? And so it's raising a bunch of questions. And then the second part is shifting the perspective more towards technology management, history of science, philosophy of science kind of perspective, to see, okay, what, you know, is this an outlier, or is this kind of a normal development? Have we seen this with other technologies? Does this follow a certain pattern? And then we're going to loop it back after having looked at some of those tools, to some of those different lenses we can use to look at this problem. We're looping back to the fusion problem. All right, so that's a bit of the map, the outline. So that's, let me share my screen, and then we can dive right into it. Okay, can you see that?
Yep, looks good.
Yep. Okay, very good. Okay, so this is the first part I mentioned, and I wanted to start with this general question: what is nuclear fusion? And in nuclear fusion, I like sort of this image of, we have two magnets of the same poles. So these are our positively charged nuclei, positively charged because of the protons inside of them, and we want to bring them together. And if we bring them close enough together, they will start to become attractive. That's where the magnet picture breaks down. And once they become attractive, they will shed some of their mass. So the resulting product will be slightly lighter, and that mass will be released in the form of energy. And it'll usually, there's different ways of getting it released, but usually the actual fusion product is not stable, and so there's it kind of breaks down into another configuration rather than the parts that came in, and then those parts have like high velocity. So the energy is transmitted to the fusion products as kinetic energy. And so the original fusion models emerged during the 30s, 40s, and 50s, and they were very heavily inspired by the sun, right? And so the idea is, in the sun, you're having very high temperatures. So, you know, if you have a block of ice and you heat it, it melts, and then it'll turn to steam, and then eventually it'll turn into plasma, which is kind of a hot gas, right? And so that's basically what the sun's made of. And so you have all these plasma part, these nuclei, then in the plasma, these positively charged nuclei racing around and occasionally bumping into one another. And so the idea is, again, you have this magnet picture. If they're bumping into each other, if they're fast enough, then they may get close enough to one another to actually cause a fusion event. So that's like the fusion explanation in a nutshell. And so this is this kind of the idea. And in the sun, the temperature, actually we saw it here, and you have a distribution of temperatures relative to where you are in the sun. And even at any particular point, you have a distribution of temperature, because in the gas, the temperature is never, the plasma is never just one temperature. It's always sort of a distribution. And so then you care about the ones at the tail of the distribution, that ones, the nuclei that are hottest, because they're going to be most likely to fuse. And so that's the picture. So there are some intricacies with these different distributions where you are in the sun and so forth, but the basic physics is fairly simple. You get particles fast enough to bump into one another, and they fuse. And so this is actually an excerpt from Zach Harvick, an MIT professor who works on fusion, who sort of summarized sort of the main variables here, which are known as a triple product or also as the Lawson criterion. These are the main variables in classical fusion picture to tune fusion to get better performance. And so it's density, temperature, and the confinement, or the time of confinement. And so in the thermonuclear fusion approaches, you would then increase your plasma density, plasma temperature, and then keep the whole thing as such for as long as possible. And so that way you can get, so this is sort of depicted in this graph here. Here is the temperature. KV can be converted into this would be about 100 million degrees centigrade here. And then here you have the density, which in the sun comes from gravity. And so people have then basically declared this then a roadmap for the commercialization of fusion. You want to get into this upper corner where you're hot and dense. And so far, you see these different points represent different plant designs. So far, people haven't really made it all the way up there. So that's like the traditional race for fusion that's now widely covered in the media. And so then we could look at this into a bit more detail. This is sort of the physics model. It's actually fairly simple model. We're going to see more complicated models later. But what I mentioned, you have the two particles here. In this case, two deuterium nuclei coming together, and then they're breaking up again into other products, but products that are lighter. Okay, so this is the Fusion 101, a quick overview. And then, so where does the idea of solid state fusion come from now? What is the motivating rationale? So if we go again to our thermonuclear fusion plant, it's basically an emulation of the sun, right? But the sun that has the gravitational potential, because it's so large, to help with density. We don't have that on Earth, so we are hotter. So if you noticed, it was 10 million degrees centigrade in the sun. Here it's 100 million or 150 million. This is sort of how people try to compensate. But basically, the idea is to build a sun on Earth. And so the sort of other extreme would be to look at can you have fusion in the gas bottle? So if you go buy like one of those gas bottles at Target for like actually no, you can't get those at Target, but like with the hydrogen gas from a supplier, then you have deuterium or hydrogen molecules in there. If you buy a normal hydrogen gas, there's, I think it's 0.02% of it is going to be deuterium, but you can also buy the deuterium by itself, and so you have these molecules and pairs of deuterium atoms, and the kinetic energy for them would be equivalent to about 1 eV, because they wiggle around a little bit. Again, if we go back to our fusion plant, it's 10,000 EV, so we have much less energy between them. And so here you would get a fusion rate, if you look at any two nuclei in your thermonuclear reactor, of 10 to the minus 5 per second or higher. And here the fusion rate has actually been calculated as 10 to the minus 64 per second per deuterium pair. So we can calculate a spontaneous fusion rate for a gas bottle at room temperature. It's just incredibly low, right? And so, but that's sort of that's in a sense the starting point why people think this is not a worthwhile idea to look at in the first place, because like how much would be different if you not just have a gas bottle, but you put the gas now inside a metal? It's still room temperature, and it's still ambient pressure and whatnot. But well, we'll have to see about that. This is what basically then the solid state picture looks like. So you have now, here there's depiction of some molecules, some individual deuterium atoms. And again, deuterium is just an isotope of hydrogen. It's just it basically is, it's what people associate with heavy water. So if it combines with oxygen, you have heavy water, and you could even drink it. People describe it as kind of sweet, but you know, it's what people like in fusion, because it because the extra neutron in there facilitates many kinds of fusion processes. So we like to work with deuterium instead of normal hydrogen. So anyway, here you have the hydrogen, or the deuterium rather, sitting in between spaces in a lattice. Now this could be a titanium lattice or a palladium lattice, or any kind of lattice, and they sit in between there, just like carbon atoms sit in between an iron lattice in steel. And so here again, sort of the solid state fusion claims, or the Lehner claims, are that you have a much higher fusion rate than the 10 to the minus 64 per second. So compared to your gas bottle, right? So that's the sort of the puzzle, I suppose, and the motivation, the claim in a sense, and the notion that maybe a solid state lattice, a solid state environment, might help with fusion, that is actually quite old. So here's the Nature paper from 1927. This was actually first published, this idea, in Naturwissenschaften, in a German journal, 1926 in German, then in English a year later by this chemist Panet. And he proposed already that maybe using a palladium lattice could help, because palladium is a metal that's particularly susceptible to absorbing hydrogen. And so there's already the idea, before fusion was even properly understood, that maybe a metal lattice could help with fusion. And then there was like some controversy around whether what they reported, whether they measured whether the measurements were accurate and so forth. And so here's just a little more detail on sort of these systems that we're now interested in, than the metal hydrogen systems. So you have like here, for instance, on this side of the metal lattice, you have a gas, and the pairs dissociate and go into the lattice. For instance, if you apply a mechanical pressure, and then on this side you have an electrolyte like H2O, kind of, like a liquid with salts in there, and then sort of you can drive them electrically, and they also you push them into lattice. So that's kind of how you get them in there, in a sense. Another way is to use ion bombardment, where basically you heat a gas to ionize it, and then you can accelerate it, and then you have like a beam. Looks like a beam of light that basically shoots these small nuclei into a material. It's a technique that's usually used for coating materials and so forth, but it can be used for embedding hydrogen in a lattice as well. So that's how you get these structures. And then there are other features, like there's dynamics. So now we've seen a little bit, there's like the composition and the structure of these lattices, but there's also dynamics. So the lattice can move and vibrate, and people have calculated and measured the frequencies. These are very high frequencies because these are very small structures. And actually, I recently came across these very cool videos where people have an extremely high frequency cameras at femtosecond temporal resolution, and so that you can see these so-called phonons, these lattice vibrations here in these different lattices. You can see them by here and this side and this side. They look like basically like waves that are going through a material. So these are, I just want you to sort of appreciate a little bit sort of these environments, the complexity of these environments in terms of structure, composition, and dynamics. Okay, so that's what we're dealing with. Okay, so now you've gotten an idea of the rationale, what people think is interesting, why they might think it's interesting. So do we have potential evidence? What is the potential evidence? And so here, a very famous experiment is 1989, Fleischmann and Pons, two electrochemists, who had this setup here with the center was sort of a small palladium rod in a liquid electrolyte. which contained heavy water, mostly consisted of heavy water, and then the deuterium was driven into the palladium now through applying a voltage, and then there were like temperature sensors around, and so the temperature sensors were calibrated such that a certain temperature could be mapped to a certain power input or energy input in equilibrium, the other way around. So now here you have a so here you have over time the temperature response of the cell. The applied potential and current was constant, and the applied input power, and then the output power that this temperature change corresponds to then fluctuated, and had this sort of large excursion, 16 degrees centigrade increase. And so if you were to then, if you map the temperature to power, and then you accumulate the power over this period, then you get the total energy measurement. And so the total amount of energy, it was 20 megajoules. This is about 5.6 kilowatt hours. And so 1 gram of hydrogen releases about 142 kilojoules from chemical combustion. And so they would have needed about 2 liters of heavy water, but they only had about 20 milliliters. So there was a much larger amount of energy measured than would have been expected from purely chemical effects. And so that was the key sort of claim and sensation, which also led them to suggest that this was of nuclear origin. And then afterwards, you may know some of this, there was a big back and forth, and people pushed back and said, this is outrageous, this can't be, we don't know how such a thing would occur, or you made some measurement errors and so forth. And this could be a whole talk about dissecting this sort of this communication, I would say, communication disaster, about how from multiple sides. So let's not dwell on it too much, but if you were interested, we can talk more about it during Q&A. There were other measurements that then also, so you'd say, well, can we have other types of measurements, maybe more precise measurements that give us not just heat, but other kind of indicators? And so you'd expect, if the hypothesis was correct, that this large heat was caused by fusion, and it was caused by deuterium fusion, the deuterium in the heavy water, then you would expect one out of several kinds of products, and we've seen earlier there's different ways the fusion reaction can result in products, and so there's actually three ways that are known for the conventionally in the deuterium reaction, and one of them leads to helium. And so for reasons I won't go into right now, but people expected helium to be a major source here, and so they tested for helium. And in this setup, which is very similar setup as the Fleischmann-Pons cell done at the University of Rome, they found that it also measured excess heat, the same kind of sort of heat measurements as in the Fleischmann-Pons experiment, which are seen down here. And then they also measured helium this was a closed system where they keep all the gas that was accumulating, and they found that that the amount of helium that they picked up correlated to the amount of heat that was produced in that system. Okay, so then I think another interesting result that gives us some potential information what might be going on is this series of experiments. I think this is particularly interesting because it's actually a series of dozens of experiments that were done in a similar setup again, with a little piece of palladium in a heavy water-based electrolyte. But this time, 2 lasers were pointed at the sample, and the hope of pointing the lasers was to stimulate the lattice, to cause these kind of waves, vibrations that you saw earlier in the little videos. And then these people did I think something like 40 or 50 experiments. If you count the points here, you see the number of experiments, and each time they changed the frequency difference between the lasers a little bit. And so in this experiment, there seemed to be certain laser frequencies that give a particularly high amount of excess heat. And so these were later compared with an independent paper which has determined the natural frequencies of the palladium deuterium lattice, and so there was quite some overlap. So that is an indication that prompted people to think that these lattice vibrations might be relevant here. Let me move on to sort of more recent results. Many of you may be aware of these groups in Japan that have some of which have joined together to form this company Clean Planet. And sort of one of their setups is basically a pressure chamber here, in which they fill these pellets, and then they first of all they do like also calibration to map the temperature of their thermometers that measure the chamber to a power correspondence. And so the calibration curve looks pretty good. They did two types of calibrations here. One with the actual sample material that they want to use for fusion, but not with hydrogen, but with helium gas. And then one with hydrogen, but with a material that doesn't contain the palladium particles. And so the actual, let me jump here. This is not a picture of their papers. I haven't seen a nice electron microscope picture of their samples, but this is a paper that describes palladium nanoparticles in a zirconium matrix. So this is kind of what we could expect these samples to look like. So you have a zirconium matrix, a zirconium like a structure, and then in these you have like little raisins in a cookie. You have these palladium nanoparticles sitting, and there's there's a rationale for that. We can talk about that more if you like, but there are certain sites in the nanoparticles in that kind of configuration that may be particularly suitable for fusion. If you're interested, we can talk more about that. But their results are the following. If they don't, in their control runs, they heat the system and they get an equilibrium temperature, which is the temperature that would be expected based on the calibration. But if they have both the palladium nanoparticles in their samples and they use the hydrogen, then they get this sort of big kink here, this bump, and so that difference here between the calibration and the active run, that is the reported excess heat in their results. And so you see it's quite significant. So it's over 100 degrees centigrade here of difference. And again, I've dissected a little bit. I mean, these are all numbers from their papers. I've just sort of tried to spell them out a bit more clearly, sort of what are the amount of sample material they use, and also what would that mean in terms of again, this chemical limit, how much would this be explainable by a chemical reaction. But in this case also the chemical limit is exceeded by a factor of 3,000. So again, there is reason to believe that there may be a nuclear fusion or nuclear reaction happening here. Okay, so this was just sort of a bit of a review of why people think solid state fusion may be a big deal. Okay, so why is this not discussed more widely then? And basically, here's just the short answers. There's been a lack of explanations that are accepted widely, and then there are remaining ambiguities in the data and their interpretation. And so, so here this is also a calculation still for the Japanese results. This is basically just to say the Japanese results suggest that the fusion rate in their experiments is 10 to the minus 10 per second. And now, if you remember earlier, we said in the gas bottle is 10 to the minus 64 per second. So that's a 50 order of magnitude increase over what would be expected. And that's actually the same number that was estimated for the Fleischmann and Pons, or a similar kind of ballpark that was estimated for the Fleischmann-Pons anomalies. And so basically this puts us on this kind of a line here where again here this is the expected fusion rate from like the traditional conventional fusion theory for deuterium pairs in a gas bottle. And then this is sort of what we are trying to explain. And there are in fact mechanisms known, and that was already recognized in the early 1990s when the Fleischmann-Pons experiments were discussed. There are mechanisms known that provide for some, that can account for some of that increase, but there is, and that is I think the big remaining challenge, there is a gap still. Even if you get 20 orders of magnitude improvement, there's still a gap, and so that gap is basically a big reason why people, many people remain skeptical about these results. These 20 orders of magnitude or maybe 25 orders of magnitude, they can be explained by a phenomenon called that's fairly widely, it's uncontroversial at this point. Actually, it's called screening, which happens when you, which is now a bit more detail about when you're what things look like when you're inside, when you have your deuterons inside a lattice. First of all, you want to get them close to each other. And in order to get them close to each other, as close, you want to have them ideally as close as in the gas bottle. Otherwise, you're already too far away. You're fighting a losing battle. To get them as close as in a gas bottle, you need to have so-called vacancies where some or sites or some defects in the lattice. I mean, in nanoparticles, you can or in certain structures, you can have other kind of defects as well, but you need to create some room for them to come together. And so, and there are various ways of doing it. Let's leave it at that. And then you can get a kind of effect from the surrounding atoms that can be maybe compared or described like this. And you remember we had this picture originally with the repulsive poles, and if you now bring in another pole, that opposite pole will partially compensate the repulsion. And so that is that kind of screening in a nutshell. So the idea is, if you have a deuterium molecule in the gas bottle, you don't have that kind of screening. You have some screening, but you don't have the amount of screening that you get if you now place it inside a metal lattice. And so the idea is, okay, here we get some enhancement of the rate, but again, not enough enhancement to really explain some of these results. Okay, so now I think now let me catch my breath and see whether there are any questions or comments, because now we can either dive deeper into the technical aspects. If people are more interested in these kind of structures and in the diagnostics and in maybe some other relevant experimental results and claims and anomalies, or we can transition more to the social sciencey side of things.
We have a question in the chat from Kira. It says, what makes a good nanosite for fusion?
Okay, yeah, I mean that, let me think about that. I could respond to that in a few minutes, or we could make it we could talk more about that. That would suggest we talk a bit more, maybe the next 15-20 minutes about the technical. Well, I don't think we have that much time for that. Let me see whether there's more interest in some of these technical.
All right, for those of you who want to do more technical, do your thumbs up on your reactions.
So, maybe I'll give, okay.
These guys want to go straight to social.
I could talk. Let me talk for just 2 or 3 minutes.
I did have one more maybe question that might be applicable to the next section too, which is like, if people are seeing these jumps in temperature, if there is these, whether there's a explained mechanism for it, why is there controversy around something happening, right? It just seems like there should be agreement that people are measuring something. So shouldn't there be interest in trying to account for that gap, account for, okay, if we considered that there's screening, if we considered that there's fusion, if we consider, like, if we added up all of the different ways in which you might account for that gap, like how might we measure them and then show what those mechanisms are? Like, it's so wild to me that there's not interest from a broader like scientific community just to say like, and not coming at it from like, yes, we know exactly what's happening, but we want to explain why there is this, like why people are seeing these measurements, that there is something that is happening.
Right. Yeah, that's a great question. Yeah, there's a couple of responses. I mean, one of them is, you know, there are a number of chemical mechanisms that can cause heat, right? And so, so there, and so some people who have skeptically engaged with the subject have pointed out concrete mechanisms, so certain chemical, and some others have actually sort of hand waved and said, well, it could be some mechanism, you know, and people say, well, I'm not an expert in this, but I think it might be some chemical mechanism, and I just don't, you know, maybe somebody said, I'm an expert in nuclear physics. I know it's not nuclear physics, so it must be something else, whatever that is, you know. So that is one way of how people are responded. The other thing is, you know, what's very important is to look at the energy, which is the total amount of power accumulated over time. Because, you know, if you have a burst of temperature increase or basically excess power, but that is only very short-lived, then maybe it is a sort of a concentration of multiple sort of chemical reactions happening in, you know, in your lattice, so kind of a concentrated release of energy, and so you can only guard against that by really running your system for such a long time that you have accumulated more energy than could potentially be the total sum of chemical energy contained in your system. I mean, people account for this typically by counting the number of atoms in your system, and you could do that by, you know, by the weight, and then you divide it by, you know, the values that you know, and then you get the number of hydrogen atoms or deuterium atoms, and then a chemical reaction is not associated with more than a few EVs, and the EV you can convert into joule. That's just another unit for energy, and so then for some of these results, people have measured such a large amount of total energy that you're in the keV range or so per deuterium atom, and then it becomes difficult to explain. But actually, I have to also say, a lot of the reported, so I've showed you some of the better data, I would say. There is also a lot of reported data in the field where people haven't run their system long enough, you know, to guard against that, to provide that defense, to say, look, the total amount, you know, and people have not been, it's also frustrating to me reading these papers, people often have not been very explicit in, look, this is the chemical limit, this is, you know, you have really sometimes have to dig for it and search for it, and so there, I would say there's a number of explanations, and I think, yeah, sometimes I think the problem is on the side of the person criticizing this by being too vague and saying, oh, it could be some sort of chemical reaction. I think one should pinpoint these people, say, what exactly, what reaction is it? And so sometimes it's also a problem of the researchers that have not run their system long enough and not pointed out clearly what the chemical limit would be. So,
Which I don't think is necessarily solely this field, right? That's like a lot of research fields where it's hard to
absolutely.
reproducible experiments, or there's a lack of like you can't even necessarily know what they did because they don't report it well.
Yeah, exactly. There's generally, this is a big, yeah, absolutely. And but this field is now, you know, and there's two aspects to this field. One is the notion that extraordinary claims require extraordinary evidence. And then secondly, I think because of the history of the field, there's even a sort of particular, you know, focus on it. There's a particularly, you know, close.
People are tougher on it. Yeah. Okay. I think a couple other folks have their hands.
I'll ask the question about the chemical reaction since you brought it up. You can hear me?
Yeah.
So, I mean, one obvious chemical reaction is that if you add deuterium to a material, it'll change the vibrational structure. So you'll weaken the bonds.
Hey, sorry, I'm late.
Oh, hi, Carl. So, and Charles, what chemical reaction would you then propose?
Well, it's a general principle. If you change the molecular weight from hydrogen to deuterium, you'll change the vibrational structure of the material,
right?
And therefore, that could weaken that. You know, the deuterium is heavier, and therefore it could weaken the chemical bond.
Yeah, but how much energy would
that's? Well,
how much energy would get released?
Depends on how many bonds are broken.
Yeah, but you could probably put an upper limit on that, you know, and say if it's less than 10 EV, you know, but then the exasite results suggest that you have, you know, 3000 EV per deuterium.
I'm not trying. I'm simply. I mean, I think this is one of the chemical reactions that have been suggested that could cause the kind of excess heat.
Right. That's right. That's right. Yeah.
So I was just asking if you had any. I mean, I'm not trying to debate it. It's not my suggestion. I'm just asking if you had any opinion on some of the. I mean, I saw the suggestion at ICCF.
Yeah, I mean, there are different exothermic and endothermic reactions, and they have to be accounted for. But the chemical ones are always going to be, you know, below on the range of like 10 EV or less, you know. And so I think that is the main takeaway here. But you're right. Yeah, there are different kind of lattice structure modifications that can release energy, and then others that can take up energy.
Well, I think that there are cases of materials that undergo dielectric breakdown and they release huge amounts of energy.
Well, there's deuterium stripping reactions where you take the neutron back off again. That can happen, and we probably don't know all the ways that could happen.
Yeah, so that would be a nuclear reaction.
Yeah, I mean, there are non-nuclear reactions that can release large amounts of energy. Usually, some sort of dielectric breakdown or other type of, you know, general phase transition in the material. If there's a phase transition in the material, it would release a huge amount of energy.
Right, especially reactions that are open to the atmosphere or something like electrolysis typically is, because there's an awful lot of oxygen and other materials around that can not be accounted for.
We need to put a limit on it as to what is a realistic upper limit, and there can be a huge amount of energy released in a short period, in a short period of time, but the total amount of energy would still be capped by the chemical limit. And so so that's, again, if you run your system long enough and you exceed that chemical limit, then that would be the strongest argument in terms of if you rely on heat as an anomaly, like as an indicator of an anomaly.
Right. I mean, if you change the whole palladium catalyst into palladium oxide, how much energy would that release? You know, not very much. And also, you'd notice it looks different.
I think Eugene has a question. Eugene.
Yeah, Eugene.
So you get from the 20 orders of magnitude difference. Where does it become significant in terms of having sustainable output from a reaction model that produces a steady state of energy release? I mean, you're looking at something between a subcritical mass, a critical mass, a alpha beta decay type of scenario to where is that line that you need to cross to be significant in terms of energy production?
Sorry, I'm not sure I understand your question. Can you rephrase it?
Well, you know, random events that you're in a gas bottle versus a fusion reaction in the traditional sense. At what point does this become a technology that's useful between those 2 points?
Yeah, I mean, if you imagine a cubic centimeter of palladium, then you can fit about 10 to the 23 deuterium atoms in there. And now if you have a fusion rate of 10 to the minus 10 per second, then you have, a very large number of, you multiply the two numbers, and the 10 to the 23 is much larger than the 10 to the minus 10. And so you have a very high observable fusion rate. So the 10 to the minus 10 per second that has been estimated to be the rate in both the Fleischmann-Pons experiment and in the Japanese nanoparticles experiments, for instance, that is a rate that is both observable and technologically interesting. I mean, I can show you and send you some back of the envelope calculations of sort of how much energy you can get out of a certain system per day and so forth. But that is definitely, the 10 to the minus 10 is a worthwhile goal to shoot for. And 10 to the minus 20, I would say, is kind of the lower limit of the interesting kind of fusion rate. So I think that range, 10 to the minus 20 to 10 to the minus 10, that's what we want to shoot for. And 10 to the minus 64 is kind of the baseline of again, the gas bottle. Yeah. So we need a 40 to 50 orders of magnitude enhancement.
What are the ideas? You're going to get to this in the presentation. What are the ideas for achieving those conditions where that's possible?
Yeah, so maybe we should move on with the presentation and get a bit more into that. Okay, so and then maybe I can stick around later to answer questions in the chat.
That sounds great.
Yeah. Okay. So I'm going to loop back into it. So if you indulge me now, so I will go into a bit into the social science aspect, and I will loop back into and sort of close the circle, because in a sense to these to really the big elephant in the room is this explanatory gap of 30 orders of magnitude. And I think to really appreciate other ways of approaching it, I think it's helpful to sort of get a bit of a meta perspective as to how different fields might look at the same kind of phenomenon, at the same kind of problem from different angles. And we'll look at particularly the field of nuclear physics looks at the fusion problem differently than the fields of quantum dynamics. So those are the two fields I want to sort of shift the perspective from the two-body collision of nuclear physics, where we started from these sun-based models, right, to a quantum dynamics model, which views the lattice much more like as a kind of a wavy kind of ocean type of thing, where you have small waves that sometimes combine to larger waves and so forth. It's a very different perspective, even though we're talking about the same physical system. But we always have to have models and images, and these two disciplines choose very different models and images. And so that's sort of where we're heading. So now let's take a step back, and I'll talk a little bit about sort of these questions at the heart of the history and philosophy of science, I would say. Okay, so this is part B. Hold on, I got just kicked out here then. Actually, let me try to skip through this. Okay, so we're kind of starting, and apologies, some of these slides were assembled in a bit of a rush, but so two of the major philosophy of science in the 20th century is Karl Popper and Thomas Kuhn. And sort of Popper has this image of that science or knowledge builds up a little bit. I would always think it was like the cathedral, like lots of people contribute, but the overall structure is there, and over centuries, many people add a little bit here and there, and sort of it grows like a cathedral. And then Kuhn is more like a city that gets burned to the ground and then built on top anew, and then burned to the ground and built on top anew. So that's like sort of these are in a nutshell the two big perspectives of the philosophy of science of the 20th century. And now let's look at it from another perspective, a bit more concrete. So if we think about different domains like chemical engineering or electrical engineering, material science, you look at these different domains, and sort of you have sort of you can think about sort of trees of knowledge growing out of them, each domain. And then there's like an element of, sometimes you have combination. You have this incremental growth of knowledge building on, every PhD builds on whatever their advisor has done and then pushes a little farther. And then occasionally you have these combinations. So this is a kind of a theory of technology development from a guy called Brian Arthur at the Santa Fe Institute. So that there's this incremental growth, and then there's combination, and then there's recursivity of the sort of same process happening again and again. So combination creates sort of a new branch, and then that sort of becomes part of that body of knowledge, and then that new branch might grow again, and then you have other combination, and so each of these branches, they kind of grow incrementally over time. And so I would say in this picture already we can add some nuance now. I mean, there are different types of scientists involved, and this is, I think, often neglected. So there are scientists who are more comfortable working again incrementally, working, just adding a little bit to what their doctoral advisor has done, and then sort of and then building on that and adding a little bit more of that. And others are more, I would say, more reckless or more risk taking. They try to be ahead of their time, and sometimes they are, and sometimes that doesn't do so well for them. But so I have started dividing these sort of groups, or categorizing these sort of different groups of scientists that I've observed both in history and in real life into builders and scouts, and then integrators are the ones that are trying to mediate between those those that have these more like out there ideas that beyond the settlement, so to speak, and then those that are kind of advancing the parameter of the city in a sense. And so then over time, I mean, knowledge obviously is dynamic. Over time, it fills the gaps and it grows. There's an interesting literature in the psychology of science that has sort of looked at personalities of scientists. And here we're looking at personalities of scientists along two dimensions. One is openness, and the other is conscientiousness. So these are two of the 5 dimensions of the famous ocean model, the Big 5 model of personality. And so in this paper, this psychology professor, he refers to people who, scientists who are low in openness and high in consciousness as career scientists. And these are, in his argument, essential to normal science, what Kuhn called this sort of in-between process of incremental science between when the city gets burned down and built up again. And then in this paper, this psychologist refers to people that are very high, scientists are very high in openness and low in conscientiousness as creative scientists. And of course, ideally we'd have people up here in this corner, but these two traits tend to be anti-correlated. So you're either very high in openness or you're very high in consciousness. Very few people are both. In fact, this paper shows that people who are high in both tend to be entrepreneurs. And so I would say these are the kind of integrators that are connecting the scouts to the builders. So the scouts are, I think both are necessary in the process of science. The scouts are the ones that create new ideas, that create new hypotheses, that pay attention to anomalies, and the builders are they're more uncomfortable with that, but they're more comfortable with developing the better instruments, better code bases, and so I think that is sort of a model for this sort of process about how science works and the division of labor in science. Then sort of think about the temporal evolution. There's very little work about sort of phases of technology emergence. This is a recent paper. I'm not too happy with it. I've done some work in this area myself. They talk about infancy, transition, growth, but it's all not very well defined. I think really what we're looking at more is sort of this back and forth. This is what this combination, I think, looks like. This is kind of a black box in Brian Arthur's picture of technology evolution. But looking into this black box, I think there is an early phase of interpretation where it's not so clear yet whether there is the potential for a combination or for something new or not. And then there's a proof of principle, And then there's optimization and incremental improvement. And you can see that same process. I think you can apply it even to more incremental, smaller discoveries, but you can also see it apply, especially visibly, to larger discoveries where this interpretation phase is drawn out. And I'll throw in an example very soon, so that this is just a little bit of the theory background. So let's skip this. And
one thing I'd like to mention, I see a big breakup between observers, experimenters, and mathematicians.
Mm-hmm.
There are many scientists that want to observe, don't want to experiment. There are many that want to experiment, and there are many that desperately don't want any new experiments to be done because they're too busy building mathematics models.
Right. Yeah, that is a great point. And I think the makes me think a little bit about, in philosophy, there's the divide between analytic philosophy and continental philosophy. And the analytic philosophy scholars are from the UK typically, that are very sort of theory oriented, and they build up these beautiful buildings of thought. And the phenomenological continental philosophers are more about observation. And you have similar actually debates in the study of consciousness, for instance. Some people barely look at what consciousness would be, and they build up beautiful models, and other people say, let's wait with the models that study extensively what different aspects of consciousness are. And so I think, yeah, I think you're right. That is a division that manifests in many areas.
We have a lot of trouble with the string theory guys who don't care about the universe we live in. But
yeah, exactly. Yeah. The Humboldt, Alexander von Humboldt once said that the most dangerous worldviews are from those that don't view the world. And so that is exactly the sort of the lack of empirical grounding, and that's described by that. Okay, so let me transition a little bit from this theory part to now, applying this sort of theory about different models of the emergence of scientific or technical fields. And let's look at a concrete example here with the transistor, which I've studied quite in detail. And so this is one of the graphs from a paper I have I'm working on that sort of shows here the number of semiconductor publications over from 1900 to 1960. And you can see there's a big takeoff here in 1948. This is where the point contact transistor was announced to the public. And then, about in the 1950s, a couple of years later, you had the first transistor products with a small lag. But what's most interesting here, I think, is this. There's thousands of papers in total, in some, of semiconductor papers before 1947-48. And if we also look closer at what this activity was, some of these papers were associated with patents also. So the first patent for a solid state amplification device was in 1926. There was another one in 1935. There was a paper in 1938 that had actually a working solid state amplification device, just didn't work at high frequency. But so you had this whole pedestal, this whole pre-pulse of activity before the famous point contact transistor. And actually this was also time coincident with a point contact transistor that was developed in Europe by Matar and Welker. Welker was a Heisenberg student, so we this sort of suggests we should look at sort of, I'll go more into detail in a second, but we should look at invention maybe more as a process than just an event. And we can even have we could see similar kind of developments where there's these turning points of where a proof of concept has been. There's like this long search phase of concepts and ideas, and where a lot of aspects of a new technology are already there, but they're not quite in the right parameter space, either because they didn't find it or because just the supporting technologies were not there. And then sort of you have these singularities where things take off, and where then commercialization becomes feasible. And so here, and then another aspect of this pre-pulse in the transistor field was that there's really like a lot of, you see here again these milestone designs, but but there was a lot of different types of knowledge being developed that was relevant here. A lot of sort of steps along the way in these different type of knowledge buckets, in these, and these are very different types of knowledge. These anomalies were much more practical knowledge, like almost like clinical knowledge in medicine, where people practitioner knowledge, and like the Lenner field today is a lot of is practitioner knowledge. And then you have like simultaneously a deeper development of like material science techniques and material science understanding. And then you also had a theory development in conduction theory, electrical theory, and then also quantum theory and solid state physics. And so the big contribution of Bell Labs, I think, was to recognize, and they did it quite deliberately, to recognize, to pay attention to these designs, to pay attention to the anomalies, but also to closely follow what else is going on, and then at some point decide the time is ripe to make a big push to integrate these various types of knowledge. And so that sort of this raises an interesting question from a sort of strategic point of view, whether you're a company or a nonprofit or an individual, like in terms of timing. I have another paper in the works called Timing as a Capability. And so that really depends on, so what kind of is the right strategic decision? It depends on where you're at in this sort of larger development, this larger cycle. And the question you should ask yourself is, are you 5,000 person years away from this kind of inflection point, this kind of turning point where a proof of principle design has become feasible, or are you 50 person years away from that? If you're 50 person years away from that, maybe you could launch a startup. If you're 5,000 person years away from that, not such a good idea. This is like another example for this would be Theranos, right? Like this is basically pushing back against the idea that this sort of heroic idea that you can will a technology into existence no matter what. This is much more the idea that new technologies and new scientific principles, they depend on this undercurrent, they depend on this collective cumulative development. And as an individual person or individual organization, you can understand and pay attention to this, and you can contribute to some extent at the right moment in time and push it forward. But there's limits to that. You can't just, like Theranos, will into existence something that may be possible, but that may require 50,000 person years of additional sort of groundwork to. So that's sort of getting a little bit at that point. Again,
there is a question.
Mm-hmm. Go ahead.
Yeah, hi, Florian. I guess related to this, since you've looked at the history of different technologies, what's your sense of how far this field is in terms of technology, advancement, proof of concept, et cetera? How many person years away do you think this field is at this moment?
Yeah,
I know that's kind of going to be speculation, but like where approximately, what's the magnitude here?
I mean, that's a fantastic question. I mean, I think, and that is, of course, the person years. Yeah, it's that is an interest of mine, is sort of how to think about those more quantitatively, and how do we quantify them. And see, this slide is a little bit of an advance over that slide, because it starts to allocate these person years over these relevant sort of knowledge domains. And I think we could do this. I mean, I've actually done a similar graph for the Lenner field. Actually, I don't have it in this slide deck, but I think the Lenner field also, you can divide it in these blocks of different types of knowledge, the anomaly reports, the materials, and then the theory and model development, right? And I think in terms of materials and diagnostics, we're basically there. I think I've studied the literature on these metal hydrogen systems and different sort of defects and structures that form quite in detail over the last couple of years. And there's been, in the last 10 years, there's been so much progress in this area. And I'm happy to send you a selection of papers, whoever's interested in that, to sort of what the latest, most relevant papers. But I think in terms of materials, we're there, the techniques. Now, what's missing most is the kind of guidance from theory and models, and how exactly do you want the materials to be tailored? So that is where we have the biggest gap, I think. And so, but I think here what's interesting, and again talking about sort of the convergence of different fields, there is and I'm also working on an article about this sort of together with a student, which is actually supported by the Anthropocene Institute, which I'm grateful for, about this sort of how quantum engineering is sort of is now sort of taking off in respect to energy applications in different subfields. So there is like a whole in solar cell engineering, there's more and more quantum engineering creeping in, actually taking inspiration from photosynthesis, which has this extremely fast energy transfer process built into it, and so people now apply this to the engineering of organic solar cells to make them more efficient. And you also have in the battery domain, you have people working on quantum batteries, exploring similar kind of quantum engineering mechanisms. And then in the nuclear field, you have people starting to think about nuclei as qubits. And so in each of these fields, you have they have the same mathematical formalisms apply, and each of these formalisms deal with the enhancement, the acceleration of transition rates of quantum states. And so some people have called this coherence engineering or transition state engineering. And so I think there is a field growing now that provides the right kind of tools and code bases and skill sets that are needed in this bucket, in a sense, the theory and models bucket. And I think in terms of anomalies, I think we are also there in a sense, we have enough anomalies to know that there is something interesting. So I do think the biggest gap is here, and I see there is momentum in it being filled. So to give you a concrete number, I think we need to sit down, maybe have a few grad students involved and to make this a little bit of a project to come with a ballpark number.
Yeah, I slightly disagree. I think that we don't actually need theory and models at all. We just need a business plan that generates revenue and profit. I think that'll happen long before theory and models, which is the same way thermodynamics went.
Yeah, so that's an interesting question, whether this field will go more like thermodynamics or more like the transistor, because like the transistor, this in a sense, you had these imperfect. This design was later built by a university group, and it actually worked as a transistor, but it only worked like 20% of the time or so. So it was not, and this one also worked, but it didn't work at high enough frequencies, and so people did not know how to which levers, which of the many parameters to turn, such as to get the optimal performance. So in this case, theory was a bottleneck, but to actually, I should also say that the theory was not perfect in 1948, but it was reasonably developed to help inform and make the reliability higher. And so maybe Carl, maybe it's a bit of both. Maybe it's a bit of the transistor and then it's a bit of the steam engine that we're looking at here.
But the story of the transistor emerged from an institution with an infinite funding and infinite lifespan. And we don't have very many institutions like that.
Yeah, but the solid state physics team was actually only about 20 people in Bell Labs. It started out as 15 people, and then at some point they increased it, and in 1946 or so it was maybe 30 people. So it was still but I think the reason why it worked so well is because they did very little, and this is contrary to their own storytelling. I mean, they tried to have this genius, the story of the geniuses, but they did mostly sourcing of knowledge from outside. So they were surveying and paying close attention to all of these developments, and then sort of and they really acted as a sort of a small, nimble integrator organization, this solid state physics group at Bell Labs. So I think there is hope in the sense that I think that there's also lessons to be learned that even as a small organization, if you're too early in an area like Theranos, you're gonna, even if then you raise all these funds and you're trying, you can't force it. But if you get the timing right, and if you observe all and you smartly sort of tap into all the different kind of knowledge that's created in relevant areas, and you recognize that you're close enough to an inflection point where you can make a push forward, I think even a small organization or a small team can make a big impact.
Okay, so without dragging the point too long, my understanding with Shockley had a pretty good concept of science right before he recruited a team with including Bardeen to create the transistor. So it seems at that point it was more of an engineering exercise rather than a scientific endeavor. And
so I would say the mastermind at Bell Labs was Mervyn Kelly, who's a director of research, and he recruited Shockley. And actually, it's good. I can't tell out the top of my head whether Bardeen was recruited also by Kelly or was recruited by Shockley then sort of as a second degree. But Shockley was actually initially working on trying to replicate. So Bell Labs was trying to replicate the anomalies that were out there, and one of the things that Mervyn Kelly did, and this is well documented, he brought together William Shockley and Russell All. Russell All was known as sort of the tinkerer. He was sort of somebody who was deeply connected with the radio amateur community, and the radio amateur community was where a lot of these anomalies were reported in Radio News magazine, for instance. And so All had known about all these anomaly reports, and he even presented a small radio with a solid state amplifier that sort of worked imperfectly to Shockley. Again, this is all documented. I can send you the references. And so this was a major impetus for Shockley, who was a basically young graduate with just a PhD. Was he at MIT or Princeton? One of those two. And then, and so he really benefited from that kind of inspiration of Kelly connecting him with All the tinkerer. And I think that's what worked really well at Bell Labs, this integration, bringing together of different types of knowledge sourced from different communities. Okay, so here we're going to go into here. Just going to dwell a few more minutes on the transistor because it's such an interesting thing. Also, this was this Radio News magazine. And in 1925, the editor, Hugo Gernsback, he wrote an editorial based on these anomaly reports saying that they called it just a crystal, these semiconductor materials. The crystal now actually replaces the vacuum tube, that this is a revolutionary radio invention, need be emphasized no further. We can not only detect with the crystal, so it was used as the diode already at the time for radio, but we can also amplify with it. The oscillating crystal also explained how some radio experimenters have been able to obtain such remarkable long distance records with crystal outfits. It would seem that wherever these records were made, the crystal actually oscillated in one way or another without the user being aware of it. And so, so this was kind of the prediction of the vacuum tube being replaced, but this was 20 years too early, right? So that's sort of also an interesting. And he actually says later in the editorial, well, I no doubt there's much work to be needed. This is just a laboratory curiosity for now, but I have no doubt that eventually we'll get there. And then, this is even a couple of years later, Wolfgang Pauli, one of the most famous physicists at the time, he told his student Piles, one shouldn't work on semiconductors. That is a mess. Who knows whether semiconductors even exist? And semiconductor physics was known as dirty physics, the physics of dirt, because these materials were known to be very difficult to control. And the reason was basically, let me jump ahead here. The reason was basically that what people used as early semiconductors for these diodes were copper oxide compounds. And so you had these sort of messy compounds with different ratios sometimes of the different stoichiometries, and then also let alone different different impurities in there. And so it was a major step really to move from these messy compound semiconductors with unknown impurities to these
cosmic rays,
to these highly controlled single crystal kind of samples. So the other aspect was that these were polycrystalline materials. So you had sort of different grains, and every grain had sort of different sort of concentration of impurities and so forth. So what was needed in this material science bucket was to first of all to recognize that single crystals are just much more controlled samples than polycrystalline materials, and then elemental semiconductors are much more controlled than these compound semiconductors. And then there was this careful work done also by different communities around the world. This is from a German paper of sort of what is the relationship between the percentage of impurities, this is now copper and germanium, for instance, to the free charge charge carrier concentration. And so it was all of these sort of tedious work that was required before then the kind of samples could be created that would correspond to the band gap theoretical models that also were developed. Originally you had sort of models of a single atom with the discrete quantum states, and then if you put many of them together, then you get these bands, right? And so from that you can infer what the conduction behavior is of the material. So it was really, there's all these insights required to get samples to be controlled in a way that would yield reliable results, and also to understand what parameters would really matter and what the relevant parameter range would be.
Yeah, well, the clean room was only invented around 1960.
Right. Yeah. No, these were done without clean room. If you actually look at some of the this was the famous point contact transistor, of 1947, 48. It was basically bolted together. This is a shard of germanium, but this is a single crystal shard of germanium, prepared at Purdue University for specifications, with the controlled degree of impurities, and so yeah, this is coarse kind of work, but there was there went a lot of detail into getting the sort of this uncertainty and lack of control out of the way. And then the design itself was actually quite simple. And that was also design that was anticipated already in the 1920s. Okay, so this is just a little bit on here I had some plots about sort of these anomaly reports. These are from papers from the 1920s, early 1920s, where people saw these negative resistance effects, these amplification effects. And so, yeah, that's just a pictorial representation of, again, the different anomaly reports. And also here, I want to represent the different levels of ambiguity. So the red bar means high ambiguity. If some aspects of some of these types of knowledge were lower in ambiguity. And by ambiguity, I mean sort of, here I had like a little example. Just people use this in neuroscience and psychology and stuff. So you have this if you have an unfolding phenomenon, when do you make a judgment call as to identify or interpreting it, and so this is in a sense what a manager like Mervyn Kelly faced at Bell Labs. Like, do you wait when you have all these sort of different developments? You have sort of a clearer and clearer picture, but there's ambiguity along the way. Each of these results may have some ambiguity. Maybe some of these results are just a measurement error, but sort of you see this unfolding picture. You see more and more dots emerging. When do you make that judgment call and say, okay, I think there is something here. Let's double down and expand the team, or let's wait a little bit longer. We need more data. And of course, every entrepreneur faces that choice, right? Because if you make your judgment call too early, then you may be wrong, and you may think this is a cat rather than a rooster. But if you wait for too long, then everyone can see that it's a rooster, So that's of course again this question of timing, and when do you decide to double down? Okay,
so it depends on when people decide it's relevant or important, and usually people decide whether it could be important way before they know what the heck it is.
Right. Yeah, that's why I had the economic demand section in here as well. Like it was also, I mean, there was a big demand pull in a sense in the 1940s and 50s then for switches, and so people were paying a lot more attention to these anomalies after they realized, well, we're going to need an awful lot of vacuum tubes, and we're not sure that's the best idea of doing it.
Yeah, there's something called demand push too, where a company that's making an expensive product doesn't want to accidentally make a cheap one.
Right, yeah, exactly.
You get a momentary reprieve from that in wartime.
Right. Good point.
So Florian, how unusual is Clean Planet as a concept to execution from a consortium of academic and corporate research projects to where they are now? And Is there a potential for something like that happening in other places?
Yeah, I think it's not uncommon. I mean, there is especially in pharmaceutical industry, you often have consortia that engage in early research and then later that later then form a company together. What I think is unusual or surprising in a sense is that and maybe Carl is right. Maybe they are able to bring a product to market without fully understanding how it works, and maybe it works well enough for them that what they have found with this admittedly very careful and tedious work over the years of sort of phenomenologically, empirically refining the performance, maybe that would be good enough, but maybe it hasn't. I mean, it really it's hard to say, because I mean ultimately the prime way is, I think, to have a model and use the model then to simulate what's the optimal, the optimal range of parameters and the optimal, say, composition of materials and structure and so forth, to really to have an optimal implementation, what we call it in the management dominant design. And so that would be for me the most surprising and most remarkable thing about Clean Planet, if they're able to successfully commercialize a product without having been able to systematically optimize it.
Thank you.
Okay, so I think we can close up, we can wrap up this, let's wrap up this transistor section here. Actually, this is getting it just a little bit more in this, okay, 3 more slides on this, in this sort of interpretation domain. So, when we look at the phenomenon, I love this sort of study that researchers have done, where they asked people to look at an image. People looked at this image, and then they studied their eye movement. And so free examination yielded this kind of pattern where people paid attention to them. And then they gave the people in the study different goals of give the ages of the people, given tasks. And so in a sense, the perception of the image, the intake of data was then shaped by the priming in terms of what people were looking for, right? And so again, if we come back to the sort of philosophers of science like Kuhn and also later Paul Feyerabend, their argument would be that theory determines what perception, the perception observation is always theory laden. And so and there are different kind of angles, different things we can focus on when we study a phenomenon. And we always have to do reduction. We always have to focus on something. We cannot never take in the full phenomenon. We know this from, like, for instance, when you create a map, you cannot make a map that's 100% representative of your object. But you always have to pick what you think is important, what is not important for your purposes, and what you pay attention to. And so and this is from a textbook in engineering systems, a multidisciplinary field I'm also affiliated or associated with. And so here is this notion also, you can have different levels of abstraction, you can have different viewpoints. And so applying this to the fusion problem now, and this is now where we're coming full circle. Here I've sort of taken this, I've divided this into 3 different fields. Now, the fusion problem, what we've discussed so far is really the atomic physics perspective. We're looking at a 2-body problem where these 2 bodies bump into one another, and we haven't really considered so far the internal life of the nuclei. So in the sun-based fusion model discussed earlier, it's all about these 2 neutrons just bumping into each other with enough force. And then there's a nuclear physics picture, which is has a finer resolution. It's more fine-grained. People zoom in more and look into the insides of the nuclei. And then there's another picture, the quantum dynamics picture, where people look both high resolution and with a wider field of view. They looked at not just as the 2-body system, but at sort of the environment as well, and the couplings between the nuclei and the environment. And so this is just an example of now looking at a phenomenon, an observation from 3 different angles. Okay, and so and so here, you know, there's different degrees of abstraction. So you can look at an atom. You can have this kind of picture of an atom, or you can have that picture of an atom. I mean, both are going to be wrong, but this one is probably going to be closer to the truth based on what we know than this one, in terms of how the electron structure actually is arranged and organized. And similar for nuclei. So nuclei are often represented as these little agglomerations of billiard balls, but they're much more like wave structures. And actually, this is a very cool. Oh, too bad. This is a video. It's not. I haven't copied it properly, I think. Oh no, let me see. Maybe. Oh no, this actually does work. Okay. So here on the left, you see a state transition at the atomic level. This is now looking at the dynamics of the atoms. And here on the right, you actually see a state transition at the nuclear level. This is actually the simulation of a fusion reaction, the way it happens in stars. This is oxygen, oxygen. This is two pretty heavy nuclei. But you can see much more like this wave-like nature from this modeling perspective, and not just the billiard balls bumping into one another. And so, and then if we we look at this this is a photograph, or like not a photograph, but like an image that was taken of an atom in the lattice, and you also see it as the wave-like quality of this. And there's actually a group at MIT in the math department that have done these simulations of quantum phenomena with these oil droplets on water baths, and so that then they kind of simulate the vibrations that affect the lattice, for instance, and so you can see much more like this wave-like quality of what, and this is really what. Okay, here really one of the videos is not working properly, but I think you're getting a sense of it. And so now, if we so hopefully this gives you a bit of a sense of how there's different perspectives and then different resulting models if we look at the fusion problem. And so again, this here is the atomic physics model, the sun-based model of just two deuterons colliding with one another. And then this one will be a much more refined, much more sophisticated model of taking into account the various kind of couplings and interactions, even if they're weak with the environment. And so to get to your questions from earlier on, what do we really need to do to identify what are the causal mechanisms, what are the sites, and so we need to have more sophisticated, or rather less abstracted, less reductionist models of nuclear fusion. And I think so. These are the kind of models that are more relevant here. Okay, and so this is what I referred a little bit to this different fields of quantum engineering, where people look at the dynamics, then how the dynamics change sometimes when you have not a system in isolation, but when you have it coupled and in conjunction with other systems. And so people have done these studies with molecules, where you have these excited states of molecules, these state transitions, and they can be accelerated by grouping them together. And people do this kind of work with qubits, or with models of with atoms that can be excited, and or couplings can be changed between them, and that changes or allows to control the dynamics with how they behave. Again, this is all in this wave-like picture. This is not in the body collision picture. And so I think this is maybe, let's maybe stop now, and we can talk more about this if there's time or if there's interest. But I think this gives you maybe a bit of an outlook in the direction I think one needs to go to better understand and appreciate what might be going on here in the complexity of a lattice, and why we might be missing things in this much too simple picture. Because the people who are most skeptical and about this gap, they would say, well, in our picture, we don't see how this gap could be filled. But they apply that same model for a deuteron pair that sits in this environment than a deuteron pair that sits in this environment. And so then the question is that even justified, or are you missing a lot of the parts that are relevant here? Okay, I think let me stop here, and then we can go into more detail if you like to.
Thank you very much, Florian. That was a very impressive hour and a half lecture. We do have a couple of questions in the chat. I think one from Eugene would ask, is Clean Planet, the company, considered an integrator in your perspective?
That's a very good question. I think they're an integrator on some level. I do think I'm missing. I do think I'm missing a bit more of like the theory perspective, and also I mean I'm not sure how much they built on yeah, they're certainly, I mean, they're the sort of latest results in material science. I think they are an integrator, but I would think it could be done better. But of course, that's easy to say from my perspective. But I think there is I think there's a lot of integration potential where we are at now. I do think, I was thinking about this the other day. I think we're like in the transistor time frame. I think we're like in the late 1930s, or maybe early 1940s. So I think we're 5 to 10 years from I think maybe 5 years from the point contact transistor version.
Okay.
Anyway, one should never make such predictions, but
don't worry.
This is for us.
You're not making any gambling books for any of us. But the colloquial, I think the wisdom is something that we appreciate, just giving your context to that. I think Kira, she has her hand raised for a question.
I don't want to monopolize the time, so if other folks have questions, please jump in. But in terms of this like idea around, okay, maybe a more comprehensive model or a comprehensive framework on the actual like where these might be occurring in a realistic lattice in actuality, and all of those couplings that happen, and understanding where this gap in designating where the different energies are coming from. Like from your perspective, looking at all of this literature, are there a set of like experiments and measurements that the community can agree upon that would help us like just identify, understand, measure, pursue figuring out what that gap is? Because like I'm just really interested if this is so, like if we have all of these different kind of camps and activities and things, and we're trying to come to this integration point, what does that look like? What does consensus around even just how to move forward come from your perspective?
Right. Yeah, excellent question. I mean, this I've skipped over this a little bit, but the question of communities, you know, I mean, here is just an example. So if you have 3 different communities: electrical engineering, quantum mechanics, material science, and then if you have certain phenomena, like say an anomaly that stretches, that has aspects that are relevant to say material science and electrical engineering, that's usually something that communities are able to cope with, or if something falls fairly squarely into one area, people. But what's been difficult both during the solid state amplification anomalies is this kind of, you know, when phenomena that sort of require some insights or skills from various different communities, and those are very often left alone. So that's also where, like, I think Kuhn is missing something. He points it out a little bit, that anomalies sometimes are ambiguous and are not picked up right away. So I think that is an important one, and I think that's what, in a sense, that what is a fundamental challenge of the Lehner community. And I think the Lehner community is not just. Also, the question is, what is the Lehner community? There is maybe not one community. There are multiple communities, and I think there are communities that are going to be central to the future of this field that don't even know it yet, you know. I think, and so the Lehner community is not only, I think, those that self-declare themselves as the Lehner community, but certainly I think that makes it very difficult to agree, you know, these sort of, to agree on. I mean, ultimately, that is the ultimate formation process of a new field, to agree on this sort of common, what you said exactly, to agree on a common foundation, on a common language, on what, and actually Kuhn describes this process as well. Yeah, and I think we're just, again, we're a bit before that. So I think I think this kind of integration of different relevant knowledge fields that still has to happen. And I think, but I think we're close to that, but I think we're not quite there yet. And so, yeah, to think about what communities are relevant, what communities will this new field in the future stretch across? That is a very interesting question, and that, of course, is a very relevant question to see who should be part of the table, who should be part of the conversation, for instance, at the conference next year. So it's a very relevant and a very interesting question.
Yeah, it makes me think of like the folks in the artificial photosynthesis space.
Absolutely, yeah.
Who are trying to do like gas evolution and understand and like really look at like what is the atomic organization and like the nanoscale organization as well,
Right.
of how these, where are you evolving very specifically targeted like ethanol, you know, if you're trying to get one type of like fuel to come out of that, and
Right.
they don't understand the mechanism that's occurring.
Yeah, exactly. I've looked into this this community a little bit as well. I've homed in on basically this transfer process. I mentioned this a little bit earlier about like there is in photosynthesis, this has been puzzling for many decades, why the internal quantum efficiency of photosynthesis is close to 100%, is so efficient, and it's so efficient because once you have excitation of an exciton or molecule at the receiver end of the photon, it gets transported to the reaction center where the chemical reaction takes place extremely fast.
Yeah.
And that is because you have this acceleration due to quantum coherent, at least partially quantum coherent processes. And so that is similar to the way you interact with, or you couple qubits, and then it's similar to how quantum batteries are being now developed and being charged and discharged rapidly. And I think that's where I think this field will be sort of located as sort of part of a larger movement of quantum engineering applied to not just to computing. I mean, I think information science has capitalized or has hegemonized this quantum engineering to much more than, well, they're doing great things, you know, but there's a much more application space for quantum engineering. I think artificial photosynthesis is part of it, and I think what's now called the Lehner field will be also part of it in the future.
Thank you.
But in addition to that, you have, of course, material science, the whole metal hydrogen literature that I mentioned earlier, yeah, there would be a whole other dedicated session, but it'd be interesting to do that and thinking of brainstorming about sort of who are our important communities and what their relative weight to one another.
Excellent.
So Florian, I think we have some questions regarding kind of human side and also perceptions of solid state fusion, but maybe if we could have one or two more questions on technical side. I do have one myself. So I want to get back to your point about the quantum phenomena. So if we were to make an analogy between nuclear and chemical reactions and suggest that, say, a nuclear reaction is like a tsunami, whereas a chemical reaction is like a splash in the pool. What I'm trying to understand is, you mentioned there's some coupling between the lattice, which would be a chemical phenomena, to a nuclear reaction. And so the suggestion would be that these splashes would somehow overlap or interact in a way that would cause a tsunami. But intuitively, that doesn't seem like something we would see. Is there something in the literature or experimentation you've done that would suggest that such a coupling would occur?
Yeah, so at the atomic level, you have, and actually people have simulated this with these kind of water splashes, where you have even very weak sort of splashes that cause phase transitions, state transitions that are quite large. And I mean, I think the most vivid, maybe intuitive image is actually, you know what, like even here, these kind of transitions in photosynthesis there's the couplings are often much weaker than the energy that's being transferred. And so, yeah, classically, that makes not much sense from if you think about radiative transfer, where the energy that transfers has to go into the medium that transfers it. But if you think about the medium, the disturbance much more like as a fluctuation, as a perturbation, then it makes more sense. And so there's a whole literature on using classical analogs to simulate or to illustrate quantum mechanical, quantum dynamical phenomena. And so one of them is where you treat you use a pendulum and oscillator as a counterpart to a quantum system with two states, and then the energy, the total energy in the oscillator is the state transition probability. So originally you're at 1 and eventually you're at 0. And so now if you have two states that are coupled, then you would basically think about one pendulum being excited, and then in this case, you start out with the orange one excited and the blue one is not excited. And so the coupling is the spring in between them. And in this case, you can see that the energy or the state occupation probability in the quantum sense, it moves back and forth between the two. And so here you see the full image, and you see the energy that's in the coupling in the connecting spring is always quite small only. So you have large energy that transfers from one oscillator to the other, even though the connecting medium is always only occupies less than 10% of the total. And so in photosynthesis, for instance, in these other quantum transfer processes, you sometimes have not just 10%, but the coupling is maybe 10,000 times weaker than the energy that's being transferred. But so then it depends on on how long your coherent state. This is all associated with the notion of superposition. If your superposition state is maintained long enough, then even a very weak coupling can transfer a large amount of excitation. And then the other thing is, I don't know where I have it here. There is a phenomenon known as superradiance, and then that's been extended to superabsorption and supertransfer. These are all kind of enhancement mechanisms that follow from multiple sort of independent small quantum systems, small energies to pool up temporarily, basically. And so people have also done some interesting papers where they studied rogue waves. Rogue waves are still not very well understood. These are actual physical waves in the ocean, but there's also a connection between those and these quantum phenomena. Imagine you have an ocean with many, many small waves, but under some boundary conditions, the many small waves can team up for a short period of time, temporarily form a very large wave. And then they sort of fall back apart. And that's basically some of these collective quantum phenomena in a nutshell. And so imagine you have these kind of weak couplings and weak transfer, but because you have an alignment of many of them, you have to have phase alignment, and so that depends on the boundary conditions. And if you have excitation, for instance, by a laser, you're likely to get that. Then you could have, even though you have weak couplings generally, for a very short period of time, a very strong coupling. And so again, energy is conserved in this kind of system, but and for the nuclear processes, that may already be enough if you have a strong this intensification of the coupling for just a short period of time. And there's other interesting examples. For instance, in quantum biology, where again, sort of the notion of like a small perturbation affecting a nuclear state is a little bit. People think about it. You could think about it a little bit like a fly hitting a big stone, right? And the fly is not going to do anything to the stone. But if the stone is set up in such a way it's kind of on edge, then even a fly will affect its state, right? And at the nuclear level, that is a little bit like you have to have two nuclear systems that are these massive systems that are unaffected by small perturbations. But if they're both resonant, if they're connected, at least temporarily, then you can have sort of a very delicate balance, and even a small perturbation can sort of can move energy from here to here, you know, and that can cause further dynamics down the road. And so it actually, this is from a paper by an Oxford professor on the sensing of birds of the Earth magnetic field. They have the same kind of problem because the birds want to trigger chemical reactions at the EV level with a magnetic field that is at the level of 10 to the minus 10 eV. See, now you have 11 orders of magnitude difference, where you have a very weak magnetic field, the Earth magnetic field, that now is supposed to, in the bird, trigger a chemical reaction. So that's kind of almost a similar ratio as what we're dealing with, where we have these very weak kind of phonons, for instance, in a lattice that we're interested in how they might possibly trigger nuclear reactions that are many orders of magnitude larger. But so there are very good. Actually, I have a separate graph here that sort of shows the ratio between those. So there are, I think, very good and convincing and helpful examples that point the way.
Thank you, Florian.
Cool. Any more technical questions? We have more time for one more technical one. Okay, we will move on to the social ones. So Grant had asked, Florian, what originally inspired you to start your solid state discovery journey?
Oh, good question. I have an old friend and mentor who's an American scientist in Berlin, and I met him, I suppose, first in about 2005. And his father was actually a professor at the Institute of Advanced Studies in Princeton, and a friend of Gödel's. And so this is a very interesting guy, interesting kind of quirky kind of family. And I remember he told me he was in love with Freeman Dyson's daughter, and like, you know, it's those kind of interesting connections. And he connected me when I did my undergrad in Hong Kong, and I once I took a train from Hong Kong to Berlin, and I stopped by in Beijing, and he connected me with a professor at Tsinghua University in Beijing called Xinzhong Li. And he's one of the gray eminences of this field. He's retired now, but still active. And I emailed Professor Lee, and he received me at Tsinghua University, and we spent the whole afternoon together. And he told me about his research, and I became fascinated in it. And then when I got to MIT, I found out about Peter Hagelstein being here, and so I think through my mentor in Berlin, and then Professor Lee, and then Peter Hagelstein here at MIT, I started to get more and more involved in this field.
All right, how do we recreate that, Grant? How do we make more Florians? Taking a train from Hong Kong to Berlin.
I mean, I think, yeah, sometimes, I mean, there is an interesting element about like people, like this sort of the personal connection, and a sort of it is a bit of an apprenticeship element, right? But I mean, all of these people also were people that thought outside the box, were non-conformist, unconventional, but still rigorous. I think that is such an important combination of qualities, to be willing to be non-conformist but still rigorous. It's easy to be non-conformist, but you know, and just go down the deep end, right? And it's easy to be conformist and be rigorous, but to be somewhat contrarian or you know, willing to sort of to think outside the box, and then be very rigorous about how to do it. I think that is something we should foster more.
I think also there's people that take shortcuts, like the Theranos people. You know, if you are willing to make shit up and hurt people,
right,
and lie to your investors and lie to the public, then you're probably not going to have an authentic success, no matter how much time and money you have.
Right. Yeah, absolutely.
So that might be a bad example for a science question, because we just can't deal with people that are dishonest.
Yep, absolutely. Yeah, I think so.
Mike, did you want to ask this question about the wave particle duality from the GIF within the presentation? No, you're on mute, Mike. Hello? Okay, his microphone does not seem to be working. There was a private question that talked about what are some of the more common impedances for you for this field to put together a really an experiment without interferences? Like, are there ambient things that are interfering with the experiments in this field? So I think in his case, was it cosmic rays and different things that may cause interference in the experiments in this field?
Yeah, I think most people are less concerned about cosmic rays, although cosmic rays do cause like some background measurements for neutrons and so, for instance. But so then one has to characterize that and then use that as a baseline. And so in some experiments, there can be an issue, but I think that's not the main concern in the experiments for this field. But chemistry or like material science of like preparing these kind of samples, it's always difficult and tedious, and all kinds of things can go wrong because you're, in a sense, you want to prepare these nanostructures, but you're using macroscopic processes, right? And you're mixing things, and you're like, I personally, I have great respect for people who do this. I don't have the patience, I think, to the inclination to do this kind of work. And I mean, it's easy to, on the slides, to draw these kind of diagrams of what your lattice should look like, but then have somebody actually make it and make it reliably. That's another story. But people do it, and people who have experts and who have the kind of personality and inclination to do this, they can do it. But yeah, there's a wide range. I mean, if you do it in your garage, like many experimenters have done in this field, then all kinds of things can be uncontrolled and can go wrong. If you have access to, tens of millions of dollars of equipment, like or hundreds of millions of dollars of equipment, like the semiconductor industry, you can do things much more. And you're doing something that's been done for 30 years, and and according to protocol, then you can get much different levels of reproducibility and sort of cut out some noise, so to speak, or some uncertainty. And so and then on the quantum level, we're talking about a whole other, that's then another kind of noise. I mean, now I refer to sort of noise as in sort of contamination, I would say, of your samples that can interfere with the kind of structures you'd like to create. And then on the quantum level, that's more about the dynamics. You're trying to then, I mean, it's really quite mind-blowing about what the degree of control that we've collectively as humans have gained now about creating these structures, and then also exciting or stimulating them, right? I mean, then to create these terahertz vibrations, for instance, and maintain them over periods of time in this sort of well-controlled manner. But then, then you're dealing with the problems that the whole quantum computing field, for instance, is struggling with. Then how do you prevent your environment from interfering? And one of the most problematic aspects is just heat, and heat is room temperature is heat, and everything wiggles around, and so you're trying to have this nice coherent like phase consistent motion, and then but you have particles through heat bumping into it. So everything, it is a bit of a mess, but I think also incrementally, that's what I also mean by this incremental cumulative process, is as something becomes more consolidated, there's more investment, there's more experience, there's better equipment, there's protocols building up over time, and human beings are able to do the most difficult things after a while better and better. I mean, the combustion engine is a good example, like just something that's been refined. It's a very delicate type of thing, but it's been refined over time.
Cool. This is the very last question that we have. Is there a shared facility that can be built for the community to use? Something analogous to the synchrotron facility that researchers in biophysics and other fields use?
Yeah, I think one could think about what, there are certainly I think a dozen or so of different type of machinery for diagnostics and for preparing samples and so forth that would be very useful for people to have. Yeah, one could think about it, but I think it's related to this question that was asked earlier about what is the consensus of what are the most relevant techniques and so forth. So in hand in hand with this, what we talked about, the formation of a field, and sort of this sort of shared knowledge base or consensus around the sort of what the field and the community comprises. And I think from that, so yeah, but it's a chicken and egg problem, I would say also. Maybe a facility will help in that process, and yeah. So
Excellent. All right. Thank you very much for this really informative and very, very helpful lecture. Our organization really appreciates the knowledge that you have put together on a very impressive slideshow and how succinctly you're able to communicate that. So thank you so much. So I'm going to stop the recording here.